This is AP Calculus, section 6.2, day 2 notes. So in section 6.2, day 1, we were working on rotating functions around either the x-axis or the y-axis and creating these solids that we were then finding the volume of using integration. And we're going to continue with this in this section, but now we're just not going to rotate our solid around the x-axis or the y-axis, right? Which would be x equals 0 or y equals 0. We're going to be rotating around some other axis that we're given in the problem. And so how this is going to change the math for us is just that when we think about the disk or the washer that is created when we make this rotational solid, our radius is always going to be whatever that axis is, like if it's y equals 2 or x equals 4 that we're rotating our function around, our radius of our disk or our washer is always going to be that number minus the function. And I think that when we make the picture and take a look at the problem, that will make sense. So let's just jump right into example 1. The two functions that we're working with here are y equals x and y equals the square root of x. And we're rotating this about the line y equals 1. Okay, so we haven't been given any limits of integration or any values here that these functions are between. So I have a feeling that we're going to have to identify the intersection points of these two values, and that's going to help us figure out our limits of integration. So let's start by building a picture to see what we are working with. So we'll create a coordinate plane and we'll graph the two functions that we are given. The first function is y equals x, which very easy to graph. We know y equals x is just a diagonal line through the origin. So that's going to look something like that, y equals x. And the second function is y equals the square root of x. So now I'm going to go back and I'm going to put a few little tick marks here on my x-axis and on my y-axis. So when I graph y equals the square root of x, I know that that starts at 0, 0, and then has a point at 1, 1, and has a point at 4, 2. So the square root of x looks something like this. So I can kind of see that I've got this region here that's trapped by these two functions that looks like that. And I'm also being told that I'm supposed to be rotating this around the line y equals 1, which is this line right here. Okay. So thinking about what this is going to look like, now I'm going to sketch a second picture of what my solid looks like when I rotate this. I don't know, it kind of looks like a leaf, doesn't it? When I rotate this leaf around y equals 1, what does this look like? So here's my line y equals 1. And I've got this sort of leaf shape, right, which I am rotating around. So when I rotate it around, it's going to look like that. And so I'm definitely going to have like a hole in the middle. Right? And so I get these sort of washer shapes that come from this solid when I rotate it around. You can kind of see it now that I've sketched it out. So that's what my picture is going to look like. So once again, as has been the case for many of our problems, the cross-section of this rotational solid is a circular washer. Because I'm always looking for the area of a cross-section. So I know that my area of a cross-section is going to be equal to the area of the outer circle. So pi r squared of the outer circle minus the area of the inner circle, because that's the hole in our washer. So minus pi r squared of the inner. Okay, but now I come back up to my instructions where it says that the radii of the washer will always be the number minus the function. Well, in this case, the number is y equals 1, right? That's the kind of the center of this rotational solid. So up here, I'm just going to jot a little note down for myself as I build my equation for volume that the radius of the outside of the washer, so the radius of my outer is going to be equal to 1, because that's the center, minus the outer function, which in this case is y equals x, right? So 1 minus x, that's the radius of my outer function. And then the radius of the inner is going to be equal to 1 minus, and then my inner function is that square root of x, the curved part. All right, so now that I have that, I can go ahead and I can create my volume equation, which is the same equation that we were working with yesterday. So I know my volume is going to be equal to the integral. And, oh, where do these intersect? Where is this going? Well, let's see here, right here. This is x equals 0. And right here, this is x equals 1, right? So my whole solid here lives along the x-axis between x equals 0 and x equals 1. So those are going to be my limits of integration. So volume is going to be the integral from 0 to 1 of, and then I know it's going to be the area of my washer times the height of my washer, which is always my dx, right? Well, again, the area of the washer is going to be equal to this right here. So it's going to be pi times the radius squared of my inner, or excuse me, of my outer. So 1 minus x quantity squared minus pi times the radius of my inner. So 1 minus the square root of x squared, okay? And then dx, right? Now, if this were the AP test, at this point, you could use the FNINT function on your calculator. You could totally do it that way if this were a calculator active problem. If this were not a calculator active problem, then we'd have to proceed at this point with a lot of algebra, okay? Well, how would we do that? The first thing I do is I'd factor that pi out in front of the integral. So this would be equal to pi times the integral from 0 to 1. And then I am going to FOIL out the 1 minus x quantity squared, which is going to give me 1 minus 2x plus x squared. And I'm going to FOIL out the 1 minus the square root of x quantity squared. Now I still have the negative sign in front, but when I FOIL that out, I get 1 minus 2 square roots of x plus x, okay? And then this whole thing times dx. Okay, so now if I distribute this negative right here to all three terms and clean things up a little bit, I get the integral from 0 to 1 of 1 minus 2x plus x squared minus 1 plus 2 square roots of x minus x dx. And then, as you can see, I can combine some like terms here. And when I combine my like terms, my 1's are going to cancel. So 1 and negative 1 cross out. I have an x squared. I have a negative 2x plus a negative x. That makes a negative 3x. And then I have this 2 square root of x. Well, I'm going to write it as an exponent. So plus 2x to the 1/2 power. And the reason that I did that is because my next step is going to be to integrate each of these terms. And so I want to think of each of these terms in their polynomial form, because that's going to be easier for integration. All right, so now I'm going to do the integration, and I get pi times, well, integral of x squared is 1/3 x cubed. Integral of negative 3x is negative 3/2 x squared. And the integral of 2x to the 1/2 power, again, I'm going to add 1 to 1/2, so that's going to give me x to the 3/2. So then I have to multiply the 2 times the reciprocal of 3/2, so 2 times 2/3 gives me a coefficient here of 4/3. And I want to evaluate this from 0 to 1. So now I just plug in my 1 and I plug in my 0, knowing that 0 is going to cancel out, right? So my volume is going to be equal to pi times 1/3 times 1 cubed minus 3/2 times 1 squared plus 4/3 times 1 to the 3/2 minus pi times, and when I plug 0 in for my variables, that's just going to disappear, right? Almost there. So my volume is equal to pi times 1 cubed is 1 times 1/3 is 1/3. 1 squared is 1 times negative 3/2 is negative 3/2. And 1 to the 3/2 is 1 times 4/3 is 4/3. You find a common denominator, which would be 6. So this is equal to 2/6 minus 9/6 plus 8/6, which gives me a final answer of 1/6 pi, or pi over 6. There we go. There is the volume of this rotational solid. Notice that our second example, we are using the same two functions. We still have y equals x and y equals the square root of x. But this time we are going to be rotating this sort of area, this leaf piece that we kind of graphed last time, about x equals 2. Okay, so this is going to change things a little bit for us. Let's start again with our picture, and this time we can sketch it a little faster because it's the same picture that we started with before. And we had our y equals x, and we had our y equals the square root of x, and we have this solid here that lives between 0 and 1, right? But this time they want us to rotate it about x equals 2. Okay, so this is going to make a very different looking rotational solid. So down here I'm going to make my second picture. Right, here is x equals 2. That's a vertical line, right? And I have my little leaf shape here. I can do better. Give me another chance. Let's see here. Okay, that we know looks like that. Straight line here, curved. Maybe it looks more like a canoe or a boat than a leaf, but okay. So there's the piece that I am rotating around this line x equals 2. Okay, so when I start spinning this around, it's going to create a circle like this, right? And then over here, I'm going to have another kind of boat shape. And so my cross sections, let's change colors so we can really see this here. My cross sections here that I create when I do this, once again, are going to be circular washers. This looks sort of like an alien spaceship or something like that. Okay, so it's going to kind of look like that. All right, I know, sorry, I'm not the best three-dimensional drawer, but you get the idea. If I go back here and I add in the washer on the top, you might be able to visualize this a little bit better. There we go. Okay. So once again, the cross section is a circular washer. That seems to be our common theme. And we know that when we have a washer as our cross section, that our area equation is always going to be area of a circle, so pi r squared of the outer minus pi r squared of the inner, right? But now here's how this problem is different than example 1. In example 1, we rotated about y equals 1, right? And so we left things in terms of x and we integrated in terms of x. But now because we're rotating about x equals 2, this is going to be a lot easier if we integrate with respect to y. Okay, which just means that we need our two equations to be in terms of y instead of in terms of x. Well, that's easy enough. So this one is just going to be x equals y, and this one is going to be x equals y squared, right? So there we go. Now I've rewritten my equations so that they are in terms of y instead of in terms of x. So when I think about this shape that I've created down here, my sort of spaceship looking shape, my outer function is the x equals y squared, right? And my inner function, got two eyes there, whoops. My inner function is the x equals y. Okay, so I know that because the center of my rotational solid is x equals 2, that I'm going to have to think about that when I decide what my radius is going to be. So I know that the radius of the outer function is going to be equal to 2 minus my outer function, which is that x equals y squared. So 2 minus y squared, that's the radius of my outer. And the radius of my inner function is going to be equal to 2 minus y. All right, so let's build our volume equation. The volume is going to be equal to the integral, okay, still from 0 to 1, of pi times the radius squared. And sorry, I should point out, since we're talking about this right now, limits of integration, the reason that the limits of integration didn't change is because now we're talking about the y-axis, right? But this right here, this is still y equals 0. And this point right here where they intersect, this is y equals 1. So just like on the x-axis, it went from 0 to 1, on the y-axis, my shape also goes from 0 to 1. So that is why my limits of integration are still 0 to 1. Just want to make sure that you understand that we are integrating with respect to y, but our area shape, our leaf or our little boat that we're spinning around x equals 2 on the y-axis lives from 0 to 1, just like it lived from 0 to 1 on the x-axis. Okay, so back to our volume equation. We have the volume from 0 to 1 of pi times my outer, so that's going to be 2 minus y squared, minus pi times my inner, which is 2 minus y squared, and dy, right? Okay, so just like I did in the last problem, I'm going to factor out that pi in front of the integral, and then I am going to FOIL out that 2 minus y squared and that 2 minus y squared. So when I FOIL out that first binomial, I end up with 4 minus 4y squared plus y to the fourth minus, and when I FOIL out that second binomial, I get 4 minus 4y plus y squared dy. Next step will be to distribute the negative, and then we'll combine like terms. So pi times the integral from 0 to 1 of 4 minus 4y squared plus, y to the fourth minus 4 plus 4y minus y squared times dy. So now let's combine like terms and see what we end up with here. Volume is going to be equal to pi times the integral from 0 to 1 of, well, 4 and negative 4 cancel out. And then I've got a y to the fourth term going in descending order. And then when I combine my y squareds, I've got a negative 4y squared and a negative 1, so that makes negative 5y squared. And then I have a plus 4y dy. Okay, now let's integrate each term. So volume is going to be equal to pi times integral of y to the fourth is 1/5 y to the fifth. Integral of negative 5y squared would be negative 5/3 y cubed. And integral of 4y would be divide the 4 by 2, so 2y squared. And we are evaluating this from 0 to 1. Okay, let's plug in our 1 and plug in our 0. So we get volume is equal to pi times 1/5 times 1 to the fifth minus 5/3 times 1 cubed plus 2 times 1 squared minus pi times, and again, when we plug 0 in for all those y's, that term is just going to go away. So we get volume is equal to pi times 1 to the fifth is 1, times 1/5 is 1/5. 1 cubed is 1, times negative 5/3 is negative 5/3, and 1 squared is 1, times 2 is 2. Finding a common denominator, which would obviously be 15ths here, we end up with pi times 1/5 would be 3/15ths, and negative 5/3 would be negative 25/15ths, and 2 turning into 15ths would be 30/15ths. So combining those all together, we end up with 8/15ths pi, so final answer would be 8 pi over 15. That is our volume of our rotational solid.